So in this module, we'll discuss the mean value theorem among other things. The mean value theorem is an extension, so a generalization of Rolle's theorem, which we covered in the previous module. And it's a theorem that relates the slope of the secant line of a function is defined on an interval and the value of the derivative at some point in between. So assume f is continuous on a closed interval on some closed interval AB and differentiable and also differentiable on the interior of said interval. Then there exists, so there is at least one value C in the open interval AB such that f prime at that point C is equal to the slope of the secant line, the graph of f, inside this interval. I'm sorry. All right. Okay, so the theorem, as I said, tells you that if you have a function that is nice enough, so it's continuous on a closed interval and differentiable inside. So if this is A, and if this is B, and if you have the graph of f, and look at what happens here at the endpoints. So this is, this is f of B, and this is f of A. Then this will be the secant line is this segment, and you compute the slope of the secant line. Right, the slope of the secant line is this delta f divided by delta x. Which is what you find here in this formula on the right hand side. Then that's going to be equal to the derivative at some point in between. So here there's going to be a parallel line here, so it's going to have the same slope, this one. So this line has the same slope as this one, as the secant, and that's a tangent line at some point in between A and B, and that's the point C in question. Okay, so the point C, the tangent line to the graph of f is parallel to the secant line. Right, so then the value of the derivative at that point is the same as the slope of the secant line. Again, just like in Rolle's theorem, this theorem doesn't tell you that there's only one. It just tells you that there's at least one such point. So Rolle's theorem is the case. So Rolle's theorem is a special case of the mean value theorem where f of A is the same as f of B. So which implies in that case that the point you find satisfies that the derivative is 0 at that point. So that's how these two theorems are connected. Okay, so if you look at this formula, Rolle's theorem tells you, well, I mean, what Rolle's theorem tells you is that the values of f at B and at A are the same. Then there's a point in between A and B at which the derivative vanishes, which is true. I mean, by virtue of this the conclusion, you follow the conclusion, f b minus f of A will be equal to 0, so there's a point f prime, I mean f point C where f prime is equal to 0. Okay, so kind of a corollary that we already know about. If the derivative is 0, then so as a consequence f prime is equal to 0 on AB, then under the same conditions, then f is constant on the whole closed interval. So again, questions arising from the mean value theorem involve kind of the same thing as in for the Rolle's theorem. So a typical question is to find a point C, say satisfying the conclusion of the mean value theorem for y equals x cubed, where the interval is -4, 5. And to do this, we proceed just like before, in the case of Rolle's theorem. So we are asked to find a point where the derivative equals the slope of the secant line. So what is f at -4? It's -4 cubed, which is -64. F of 5 is equal to 5 cubed, which is 125. And so what is the slope of the secant line? Is f at 5 minus f at -4. All of that divided by 5 minus -4. So this is equal to 125 minus -64 divided by 5 minus -4, which is 9. And this is just equal to 189. Okay. 189 divided by 9. Oh, what happened there? Well, this is equal, yeah, so this simplify things, this is equal to 21. And okay, so we need to, this is our target. We're trying to look for a point where the derivative is equal to 21. This is the secant line, so this is what's in the, it's on the, we find on the right hand side of the theorem, right? So we want to find a point C where the derivative is equal to that value, so 21 in this case. So we're looking for a point. So we look for a point C such that f prime at C is equal to 21, where C has to be inside of the interval. Remember that the conclusion of the theorem tells you that the point that you must be able to find at least one point inside the interval. So we need to find a point where the derivative is equal to that, and the point must be in the interval. So C has to be where C is in a comma b, which in this case is minus 4 comma 5, is in the interior. So f prime of x is 3x squared. Well, no, yeah, 3x squared, since f of x is x cubed. So the derivative is just 3x squared. So this implies that f prime at that particular c is 3c squared, and we want that to be equal to 21. So that implies that c is going to be equal to the square root of 7. Okay? And is the square root of 7 between minus 4 and 5? In fact, well, we get two possible values for c in principle, so plus or minus the square root of 7. But we are asked to find at least one. So I mean, so let me just rewrite this. We have two possibilities here. C is equal to plus or minus the square root of 7. But we need to find just one. So we need to verify the conclusion of the theorem. And the theorem tells you this one. So you can pick whichever, provided they are the lie inside the interval. And in order to check that, we need to see that, say, minus 4 has to be less than c, less than 5. And is this the case? Well, it definitely is. When you raise 7 to the squared, so I suppose, yeah, you have this root of 7 squared, that's going to be less than 5 squared. Right? So that means that the square root of 7 is positive. So the square root of 7 is inside the interval. Right? The square root of 7 just squared gives you 7. Well, this gives you 25. So that means that what's inside the square root of 7, which is 7, is smaller than 5. We already have for free that is greater than 0. The same thing applies here if we look at minus 4. Minus 4 squared would be 16, and that would be greater than 7. So C is definitely, I mean, so C plus or minus square root of 7 will do, no matter which one you pick. Okay, so C equals square root 7 satisfies the conclusion of the mean value theorem. So again, This kind of problem, these kind of problems is not very difficult. You only need to compute the secant line, so just to get this number. And this is your target, and solve the equation f prime is equal to that the number that you found, just plugging the values of f at the endpoints and computing this quotient. And then you're gonna have a number of possibilities. Discard those that are not inside the interval, and just pick whatever of the ones among those lying inside the interval, and that will be your solution. So that will be a value of c that will satisfy the conclusion of the mean value theorem. Okay, so one thing that is important here to keep in mind from now on, remember that we're gonna try to apply some criteria that we're gonna learn, and some criteria and some of the techniques we learned in the previous module to optimization problems, and later on to the graph of functions. So something that we can learn from the mean value theorem now more formally is in a more schematic way. Let f be a differentiable function on an open interval of the form AB. Then we have that if f prime of x is greater than 0 for all, for x in A, comma B, then f is increasing in the interval A, comma B. If on the other hand f prime of x is less than 0 for all values of x inside the interval, then f is decreasing throughout the interval in the interval A, comma B. Okay, so this is the test that we're gonna be using later on when we want to find out whether the zeros of the derivative correspond to local max or local min. Okay, and this theorem here is a consequence of the mean value theorem. Okay, it's just a natural thing. I mean, if you have if this were not the case, I mean, if the function was not increasing or not decreasing in the second statement, then you will be able to find points, one with a higher value than the other one, and using the mean value theorem, you will find a point where the derivative matches the slope of the secant line. And so this is the situation. Here we say that, whenever we have a derivative, have a function whose derivative is positive than the function inside an interval, then it must be increasing. If this were not the case, then we would have 2 points. One point, x1 is smaller than the other one, and such that x2 lies below, the f of x2 lies below f of x1. If not, the function is increasing. So whenever you move to the right, the function goes up, right? If not, then at some point something must have happened, it didn't go up, and you can find 2 points that go in the opposite direction. And by virtue of the mean value theorem, what happens here is that you look at the secant line, the slope here is negative. Slope is negative, so you must be able to find a point in between such that the derivative here, the slope of the tangent line, is negative as well. But that's impossible because the derivative is assumed to be positive. Since it's positive, then this cannot happen. So this can never be the case. So then whenever you have a function whose derivative is positive inside an interval or negative inside that interval, the function is either increasing in the case of a positive derivative or decreasing in the case of a negative derivative. Okay, so then we'll continue with more applications in the next video.